Hello everyone, today I'm going to show you how you can make a quartz crystal oscillator using a MOSFET and few other components. Every amplifier can become an oscillator using a feedback circuit. Here I am showing you a block diagram, amplifier with a feedback circuit, and there are some certain conditions this circuit can oscillate. So at what frequency the oscillation will happen depends on the frequency selective response of the feedback network. If I use a crystal like this one, I have a small crystal in my hand, you can see. If such kind of crystal is used in the feedback circuit, the oscillator will oscillate exactly at the frequency written on the crystal. So I am using 27 megahertz crystal, and I'll show you how you can make one. And the oscillation, to detect the oscillation, you do not need an oscilloscope. So with an FM radio, you can easily detect whether your circuit is oscillating or not.
Making an oscillator circuit at any desirable frequency is possible. However, to transmit a signal over a distance using an antenna is allowed only in certain bands, like 27 megahertz. It is called a citizen band and ranges from 26.97 to 27.4 megahertz. One can transmit up to 4 watts of signal power. In this video, I would like to show how you can make an oscillator circuit using a 27 megahertz quartz crystal and few other components like a MOSFET and other resistors and capacitors. I am using a crystal to ensure that the circuit will not oscillate at any other frequencies which is not allowed. A quartz crystal consists of a thin slice of quartz material and two electrodes which are placed or deposited on both sides. Quartz is a piezoelectric material, which means any electrical signal applied across the electrode will create a vibration in the crystal. The vibration will be very high at some certain frequency called resonant frequency. A crystal can be represented by a LCR tuned circuit with an additional capacitance which represents the capacitance between the metallized plate. At resonance, this electrical equivalent resistance becomes very low, and on the other hand, the inductance becomes very high, making the tuning very narrow. That is why the oscillation created by a crystal is very stable. If we use a resistor of few ohms in series with a crystal and use a signal generator in the circuit like this diagram, by changing the frequency of the generator and measuring the voltage across this resistor, we can find a frequency response of the crystal. At resonance, the voltage becomes very high, almost equal to that of the signal generator, and on either side of the frequency, lower or higher, the voltage becomes very low. For an ordinary LCR circuit, we will get similar response, but this range is much wider than that of the crystal. The crystal can resonate both at series and at parallel. These two frequencies are very close to each other. At series resonance, the impedance becomes low, and in parallel, the impedance becomes very high. Within this short bandwidth of the series and parallel resonance, there will be a maximum phase difference of 180 degrees from capacitive to inductive. We can make an oscillator using an amplifier easily by feeding back the output of the amplifier to the input. However, two conditions should be met. The loop gain must be greater than unity, and the phase angle between the input and the output should be 0 degree, 360 degrees or multiples of 360 degrees, so that the signal not only will be amplified but also grow additively. Now the second question is, at what frequency the amplifier will oscillate? That depends on the frequency selective response of the filter within the feedback loop. The filter will ensure that those two conditions only satisfy at a very narrow band of frequencies. Like if we place a LCR filter within this network, it can select the frequency only at the resonance frequency. I will be using a crystal as a frequency selective element with an amplifier. One of the widely used oscillator is a Pierce oscillator. It consists of an inverting amplifier. There is the phase difference between the input and output signal is 180 degrees. The frequency selective part consists of a crystal and two capacitors. These two capacitors and the crystal causes a in total of 180 degrees phase shift. Now the amplifier sees 360 degree phase shift and meets one of the conditions of the oscillation. Now we have to set the gain of the amplifier sufficiently high so that the loop gain remains always higher than 1. We can use a single MOSFET amplifier for our oscillator. I am using a MOSFET part number BS170, and there are some resistors. These 4 resistors are biasing the amplifier. Any signal applied to the input will be amplified several times at the output. The amplification depends on the output load and the transconductance, which is represented by this change in drain current versus change in gate voltage. If we wish to make an RF amplifier, we need to make some changes to the circuit. In place of the resistor connected at the drain, we can use an inductor, as it prevents or attenuates the generated radio frequency from going back to the power rail. It is also called an RF choke. To further attenuate the RF going out of the circuit, we are using a capacitor. This is called a bypass capacitor, and I am adding an additional resistance in series to limit the current, because this oscillator circuit is intended to generate very low power RF. Now to make an oscillator, we place the 27 MHz crystal between the gate and the drain. This crystal will serve as the feedback path for the oscillation. It will also serve as a frequency selective component. A capacitor is used in series here to prevent DC biasing across this crystal. The RF choke, which is 100 microhenry, represents a very high impedance at 27 MHz, which is nearly 17 kilo ohm. This is the equivalent circuit of the oscillator. As I mentioned, that a Pierce oscillator needs 2 capacitors and the crystal to get the oscillation started. The MOSFET itself has two capacitances. One is the input capacitance, that is the gate capacitance represented by Cin, and the other is the drain source capacitance, that is the Cout. At crystal resonant frequency, the crystal behaves much like an inductor. The entire feedback circuit poses now 180-degree phase difference at 27 MHz, which causes the oscillation to begin. This is the photo of the crystal oscillator. This is the crystal and the inductor 100 microhenry. This is the MOSFET. The oscillation is detected by an oscilloscope. You can see that the screen shows nearly sinusoidal wave at 27 MHz. Though it looks sinusoidal, it contains some harmonics as well. As the oscillating waveform has some harmonics, which makes it easier to detect without any scope, we can use a FM radio to detect the waveform. You can see if we multiply 27 by 4, that is 108 megahertz, which lies within the FM broadcast band. If we have a shortwave radio with a range little over 27 megahertz, we can easily detect whether the circuit is oscillating or not. And nowadays, people do not use shortwave radio. However, everybody has a FM radio inside their cell phone. Tuning at 108 megahertz, which is the fourth harmonic of the 27 megahertz, one can easily hear or detect the oscillation. In the next video, I'm going to show how to amplify and use of an antenna to transfer power as EM wave. This is the oscillator circuit, and you can see that oscilloscope probe is connected. I'm detecting the oscillation at the drain terminal of the MOSFET, and this is the power supply. And you can see the waveform, oscillation waveform on the screen, oscilloscope screen. And the measured frequency is 27 megahertz, you can see on the screen. It is almost sinusoidal. So you can detect the RF using a HF radio. I am tuning the radio at 27 megahertz, and you can see the sound at the oscillating frequency. Now you can also use a FM radio. You can see that 108 megahertz it is tuned at, and you can easily detect the oscillation by hearing the sound.
Thanks for watching. In the next video, I'll try to make a RF amplifier to amplify the signal which I'm getting from the oscillator, and use an antenna to transmit the signal and try to receive the power at some certain distance.